What's up, everyone? It's Templin. I'm broadcasting from my basement because this is pandemic 2020, but this is an introduction to high-performance computing at the University of Iowa with the Argon HPC system and the Iowa Interactive Data Analytics Service for how to access it. So, I put together this video because I tend to talk about this a lot. I tend to do this in my work, so if you work with me or if you'd like to know this is where it shows up for. This video is built to be specific to things that I find myself typically doing. It may not apply to you or your situation, but it does give a little bit of a start on how to use the HPC for two different types of analyses. One is big types of data analyses, or high performance data analyses, things that take a lot of resources or time. The other is something called high throughput, where a bunch of short analyses are run simultaneously. So to do this, I've set up a web page, and you can find it if you go to my website, jonathantemplin.com. Under quick links on the bottom right, you will find a post about this introduction to the University of Iowa HPC and the Iowa Interactive Data Analytics Service. So this post tries to give you some information about what the HPC does, where to find it, and so forth. But to use this, there are three things you have to do as a prerequisite. Number one, you need a University of Iowa Argon account. I put a link on this page to where you can request it, right there. The second prerequisite is an Iowa Interactive Data Analytics Service account. The IDAS is a service that allows you to do interactive data analysis through your browser. I use this mainly for RStudio server, so I use RStudio through the browser. But there are other types of services you can use, including Python through their Jupyter notebooks. And finally, you'll need to download one file. I have a zip folder right here, this file to download, as I'm doing right there. That one file will have all the example inputs and outputs and so forth that we'll use on the Argon system as we go forward. So let's assume you have all three of those prerequisites taken care of. By the way, this video, sort of an old school one, it's going to be replaced with the one you're watching right now a little bit later on as you go forward. So to do this, how do we begin? The Iowa Interactive Data Analytics Service, IDAS, can be found at the address notebooks.hpc.uiowa.edu. When you click on that link, if you have an IDAS account, you'll get a bunch of different links here. The one that we want to work under is Interactive Research, which you will click. So next, it'll ask you to put in your credentials for the University of Iowa. You'll get a Duo push, which I will also get. And there we go. And voila, it comes up with a screen for Jupyter Hub that asks you how you want to set up your server. These are just a few options that you have. There's some key ones that we want to move forward with. The first being, how many CPU cores? I like to give this 5. Generally, I run a lot of things that run on 4 different cores. A fifth is for additional overhead. But you leaving it at 2 is fine too. The memory limit, I tend to put 16 gigabytes in. No specific reason. I haven't really run out yet on the small types of development work I've done with it. We leave the GPU option alone, but we do go under this Mount HPC Home. And in this, we change that from a no to a yes. HPC what that means Home, is our Argon account folder system drive will be mounted to this server, meaning we'll be able to access all Argon files through RStudio on IDA. We type in demo, so we change that on demo. And this is finally down at the bottom, we change the IDAS. If we go over to the Argon Python and look at files again, you'll type ls, you'll see demo shows up in blue. That shows it's we've done all of that. Once again, 4 parts, 5 cores, 16 gigabytes. Now we're going to upload that mount file that we downloaded from our website to IDAS image to IDAS R 3.6.1. Once we do that, we hit start right over here, and it takes a little bit of time. And now we have the file up. And here we have. Next, we have to. This file is a compressed file. This is our kind of our root directory for our IDAS. It's still not RStudio. What we're going to do now is to load our studio.
Just created.
To load our studio, we go under this new menu
window. We type
we click on our studio right
demo.
here. That loads
That
up
changes the directory
our studio instance
demo.
for us to
Type
use.
ls, what we'll end
Voila,
up seeing
there
is
there is Argon demo.
.tar.
So with our studio here,
right there.
we are now able to
What we
do
can do now
R the way that we typically
is
would
stop this
in all of the other R environments that you're used to, although this is a little bit big for this video, big font. So as with any other R session, you can load packages, you can run analyses, you can do whatever. Our part here is a little bit interesting. We're going to use this version of RStudio to modify files on the Argon system. So we're not going to run R yet from this. In fact, IDAS, as of the recording of this video, which is in April of 2020, has not yet linked the ability to run Argon commands through IDAS, although that is supposed to be coming at some point soon. So what we're going to use is RStudio as a really fancy text editor to get into Argon itself. This also allows us to connect to Argon through a terminal window, which you'll see up here. So to do that, I am going to go to the top right, find my terminal window, and if your terminal window is laid out a little bit differently than mine, I can understand that. Here, to move the focus to terminal, if you go under View and move to focus to terminal, you will find this. This is a terminal window like you'd find on a Linux machine. IDAS is running on a Linux server. First, what we're going to do is log into Argon to begin with. To do that, what we end up typing is SSH. We use the SSH secure shell connection to do so. We type the option -P, the number 40 for port 40. Then we put our UIOA user Hawk ID, JTemplin, and we go at argon.hpc.uiowa.edu. Once again, that's SSH-P 40 JTemplin at argon.hpc.uiowa.edu. When we do that, it next asks us for our password. So we type in our Hawk ID password, and then it will ask us to authenticate with Duo again, two-factor. So I will push it to my device and I will approve it. And once we're in, now we are in the Argon system itself. Argon, again, is a Linux server, so I'll expand my view here. So if you're not familiar with Linux, there are a few commands that you'll want to use. One is ls, it talks about this, the actual space itself. This is my folder system in my Linux Argon instance. What we will do is create a brand new folder to put our files in. So we're going to go back to RStudio now, go back to our console, bring this up over here, move this over to the side. We need to load that downloaded file from my website onto, right here, this downloaded file, onto the Argon system. The next step will be to upload the file that we had downloaded from my website, once again under the prerequisites. So number 3, download this file. Click that, we download that to our local machine, and now we're going to upload it onto Argon using the RStudio window in our browser. So we click on the upload button, we go find this file on our disk right here for me, we click OK, and it uploads, and there it is in the Argon system. And if we type ls in Argon, we'll see it highlighted in red, argondemo.tar.gz. Now, tar.gz as an ending on a file means this file is a compressed file. It's kind of like a zip folder, but for Linux. To unzip this, we have to use a command, the tar system, to be able to do that. So we use tar xzvf as the option, and we put in the name of argondemo.gz. What it will do is unzip this file into a folder named Argon Demo, and we'll put all the files into that folder itself. So once again, the command to do that is tar, and then the option -xzvf, and then the name of the file itself, argondemo.tar.gz. So now, even though we've put it into the Argon right here, we can actually see if we type ls, our RStudio window won't see it until we hit the refresh button. when we hit that little circle in the top right of our viewer, files viewer, we'll find the Argon demo folder. So if we click into the Argon demo folder, you'll find two subfolders, one for high performance and one for high throughput. We're going to begin with the high performance folder. So high performance jobs. If you want to understand more about the high performance jobs, just take a look at the link at the very bottom of my web page. This gives an example file for the job itself. What a high performance job is a job that takes a long amount of time to run or requires a large amount of resources to run. So something that takes a lot of memory on the computer or a lot of processors. For this job, it does neither. It's an example. But basically the idea is this. We create an R file that has our analysis. So in this case, I have an R file for the analysis. You can read about it on the high performance job example page right here. But this is an example analysis. It is a unidimensional item response theory model of what's called fraction subtraction data. So data that is from a study from Tatsuoka from a number of years ago. This is not a long analysis to run. However, we're using a Bayesian estimation method for it, a Markov chain Monte Carlo estimation. MCMC is an estimation method that uses simulation to basically sketch in posterior distributions of parameters. And this Markov chain runs in serial. So each Markov chain has a series of parameters it draws in sequence. But we typically run more than one Markov chain at one time. And so what we're going to run are 4 different Markov chains simultaneously, one for each of the processors that we're going to request. So this is the file, the R file. I have borrowed the script for this from a class I taught on Bayesian psychometric models. So you can find the GitHub repo on this page, this link that's right here. But now, this is the R file. If we were to try to run this, it should be able to run in RStudio, although this RStudio won't run because what happens, this analysis requires the program JAGS. And the IDAS system does not have JAGS installed. So we can't actually install JAGS, but it will run on Argon. This is an R file that would run locally on your machine if you had JAGS installed. So that's the R script, right? So that's like writing an R program to do the analysis itself. The next file that we need is a HPC job script. The job script itself is described very thoroughly, or at least attempt to be described thoroughly on this web page here and what all the commands are. But the big picture of this command is that we are going to, I'm going to briefly walk through these to talk about them. So here, this job file has a bunch of different lines to it. The key in the job file is a little bit of formatting. Anytime that you just see a pound symbol or hashtag by itself or followed by them on this text, like you see here or here, that means this is a comment and it's not interpreted by the program that runs the job. By the way, the program that runs the job is called a scheduler. What that means, why it's called a scheduler, is because all of the users of Argon submit these job files in a certain order. And the job files line up each of what requests happen to be and put them onto a schedule on when they will be run on the Argon system itself. So the scheduler is what gets used here. The Argon scheduler is something called the son of grid engine. We don't need to get into that. But knowing about that describes what specific lines show up on this job file itself. So again, going back to this, anything that starts with a pound symbol or hashtag is a comment. If you get a hashtag and a $sign, that is what's called a directive. That tells the scheduler certain specifics of the analysis. Anything that has a pound and an exclamation point is another directive that tells the scheduler which type of Linux or Unix shell to run this script in. Unix shell commands, if you're not familiar with that, you can find them at the Wikipedia website, what that means. We're going to use the bash shell. So this is pretty much always what you see at the top. So going through this job file, let's go line by line here. At the top, you see the directive that we're going to use the bash shell. Then we see a comment that says set scheduler configuration directive. So in here, in this section between the comment I've highlighted and this last comment at the bottom, these are directives that describe what we want the scheduler to do or what specifics about our analysis. So here we have the name of the job. I'm going to leave this as is. We use the -n option for FS data analysis. By the way, you can find descriptions of each of these lines in my website link here. One thing I will note is that all of the information about this, about these different types of directives are available at the link at the top here. This is HPC documentation at the University of Iowa. So going back to the file again, we put the name, we call it FS Data Analysis. This will help us distinguish which jobs are running from which has been completed. Next, what we're going to do is tell the scheduler that we would like an email notification when our job begins, when it ends, and if it has been suspended. Suspended meaning essentially canceled in the middle of executing. So we put this line in with an option of -m and the letters BES for beginning, end, and suspension. If you did not want an email in any one of those three different parts, just take off the letter corresponding to it. So if I took off S, it would be an email at the beginning and an email at the end, for instance. But I'm going to leave all three here. The next line is something you'll have to modify. This is the email address to where it will send its notification. So put your email address here. I'm going to put mine here, jonathantemplin@uiowa.edu. But if you put mine there, then I'm going to get emailed whenever you submit the job. So please put your email address there. The next line that we're going to ask is this basically allows the scheduler to run the job, start the job in the folder where the job script exists. This is important because in the command to run R, we don't necessarily need the actual folder itself to run the job, to make the job run as needed. So this CWD option says start the job within the folder where the job script is found. And that means we just need to put our analysis file with the job script in a folder and it will find it when we refer to it later in the script. So that is the scheduler configuration directives. The next set of directives are resource directives. The first one is which queue do we run this in? So the scheduler tries to figure out a time when it's going to run these jobs. And not everybody on the system has access to the same amount of resources. And so it aligns itself into a series of what are called queues, lines of jobs that have certain permissions in. You can, so the queue that we're going to run this in is the UI queue. The UI queue, by the way, you can find more about that at this link on the source right here. But the UI queue allows you to run up to 5 jobs at once, and those jobs do not get booted by other people. So this will protect the running job itself. They're very good for high performance jobs that may take a long time. So we use UI for those types of jobs. And this job is going to take 4 cores. Once again, we're running a Markov chain, 4 different Markov chains in parallel. So the 4 cores, a core is a computing unit. Each one of those chains is going to run on each one of these 4 cores as we go forward. So that's what this option does. So those are the options for the job file. The final bit of the job file are the commands that you could run directly in Argon itself to run the analysis just from the window, the terminal window. But what happens for the job file is when it's this job's turn to run on Argon, it will run these commands as if you were typing them into the terminal window themselves. So what we have in here are the following. We have a line that says module load R. So R, by default, is not available in Argon. You have to load it first before it becomes available. It is already installed. So module load R, if you type that into the terminal window, it takes a second to run, but as soon as you do that, you'll be able to see that you can actually run R now, which is actually version 3.5.1, within Argon. So to figure out which modules are available, you can type the command module avail, and it gives you a whole list of modules. I type Q to get out of it. So we need R. Clearly, it's an R script we're running. We also need the JAGS program. So we use the command module load JAGS. This will run, create or allow us to run JAGS, the JAGS program to do the Markov chain for the analysis. Now, finally, we used the command rcmd batch. This is one of two commands we can use to run R. Rcmd batch is not necessarily the preferred one. We'll see if you take a look at the section of this video that does high throughput computing, we'll see R script. But rcmd batch, what this tells it to do is to run in R as a batch file. So basically, without having to go into R, it will run all of these R commands through R, submit this file to R to be run. So that is the data analysis file. So that's the extent of the job file. So now we want to run this job file. So to do so, we have to make sure that in the terminal window, we are in the folder where the job file exists. So we go to cd Argon demo. So we can, and we're in the high performance section of this. So cd high performance. And in here, now we can submit this job to Argon. The submission syntax is pretty simple. It's simply the command qsub and the name of the job file. So for our case, it will be dataanalysis.job. So we type in qsub, a space, the name of the file, we hit return, and it says your job, FS data analysis, has been submitted. So now if we want to check the status of this, we can type qstat-u and our username, jtemplate for me, and you can see next that it's running on the queue. Give it some more room here to be able to see it. So now it's using 4 slots, which are these 4 cores. It's running on the UI queue, and it started at 12:57 my time. So if we keep refreshing this with the qstat-u, eventually what we will see, this job takes about a minute to run, but eventually you will see that it's finished once it's terminated. And once it's finished, we'll be able to go and look at the output of the job itself. Okay, so now as we're waiting for this job to run, what you'll notice if you go to your email program, I've got my mail program up here, is that when the job ran, I got an email from root that's basically gave me the job name, and it said it started. So it started at 12:57 and 28 seconds. Then, when the job finished, sure enough, we got another email. It says job complete. Exit status of 0 is good, means it exited normally. It talks about how much time it took to run. This time it took about 4 minutes to run, I think. Actually, it's less than 4 minutes. It's a minute and a little bit over a minute. This 4 minutes is for the 4 processors, so each processor running a little bit over a minute totals to over 4 minutes. That's where that's coming from. So wall clock time of a minute 19 seconds, that's how long it took. Not something we typically run on an HPC, but it fits for this example. So now that I have this email, I can go back into Argon and look at the files that should be in the folder that is where we ran the job itself. So now we received an email that said our job had been completed. So we can now go and refresh our window, and what we should see here are a bunch of new files. Type ls into this, you can see the files as well. Here we have an error file which has 0 bytes, so there's nothing in it. We have an output file which has 0 bytes, nothing in it. We have an rout file, which if we click, we'll see the actual echo of the run itself. So this ran all the analysis. I had it output a bunch of information. These are all the estimated parameters of the analysis. Look at convergence information. Shows us the maximum R hat value of 1.02, says our analysis converged. So all of this is from our high throughput job. If we want to go and look at the data, we can load that into R itself. So we can go grab that. And now we have our analysis file already taken care of. So that is an example of high performance computing. Our next example is the high throughput example, which is a type of analysis that we use when we have a lot of little jobs to run simultaneously. In my typical workflow, this is when I use what I use for simulation studies. Simulation studies typically have a bunch of little analyses, short analyses, nothing that would take a huge high performance type of job, but they have a lot of replications, and so I need to run a lot of things all at once. So high throughput is the way that we set this up. And the good news is there's not a lot of difference between high throughput and high performance in how we could create our job file and how we create our analysis file. There's subtle differences. One of the differences is that we're going to use some commands, not only in the job file, but also how we submit it, to run what's called an array job, which means an array of jobs that run multiple times. So let me go into that to show you. So we're going to begin in our Argon demo folder right here. If you're in the, again, we're in the Linux, the Argon Linux terminal window in RStudio, IDAS, RStudio. If you want to find the folder you're in, the Linux command for that is pwd. We are in the Argon demo folder, but we're going to go into the high throughput folder itself. So we go to change directory, high throughput. So now in the high throughput folder, I'm going to just clear my environment real quick. You'll see several files. The key in all this is that we create an R file for a single replication of a simulation. So what I'm doing here is a real silly type of simulation, is to create an R file where we're going to do a unidimensional IRT model where we have 100 people as data, sample size of 100. Basically just see how well a two-parameter model recovers its parameters with a small number of people. So in this simulation, we've got a couple pieces of code that we have to create at the top that's a little bit different in R than you would see otherwise. First is this command right here. args equals, and in the R function, command args. Command args is a function in R that allows you to capture command line arguments. Command line arguments are additional options that are submitted to a program when it runs from a command line. So what we're going to do is submit to R the replication number of our simulation from this high throughput job. So what we're going to show in this example is going to run 10 replications. Each one will have a number from 1 to 10. So that running of the 10 replications will allow us to capture what the high performance, or excuse me, the high throughput job will do is we'll capture each number 1 through 10. So for each specific replication, we will know the replication number. Now we need that for a couple reasons. The first is we need to set a separate random number seed for each simulation. Why we do that is a random number seed initializes a random number generator to provide a sequence of random numbers. So if you have the same seed, you get the same numbers. We need something that we can keep track of, so we could replicate this if we needed to, but that changes for each one of the 10 replications. So here what we're going to do is create a random number seed. I'm going to start with the date, and then I'm just going to add to that the replication number 1 through 10. So now a random number seed will be different for each one of these. The next thing I need to do is to set the seed by using the set.seed function in R, where we give this our seed value from before. Now once the random number seed is set, we can replicate this analysis identically with the same number. But now we're going to simulate our data. We generate our people. We have 20 items, basically mirroring the high performance analysis that we had run previously. We have our A and B parameter generated from the A parameter from a log normal distribution, the B parameter from a normal distribution. We generate our person parameters from a standardized normal distribution, and we create our data. And here I'm going to use, again, the 2-parameter normal ogive model. For why I'm using a normal ogive, you can take a look at my Bayesian psychometric models class for a little bit more detail for that. You don't have to, but it's a nice There are certain perks to it in JAGs. Here's our analysis function. Basically runs the analysis. And at the end of the analysis, what we're going to do is I'm going to output the convergence of the analysis to see that the model converged. But then I'm going to make a comparison between the true and estimated values for my A parameters, my B parameters, and my person parameters, thetas. I'm going to make the comparison by looking at the correlation between true and estimated values, the root mean square error between true and estimated values, and the sign bias, effectively, for the true and estimated values. Each of these provides a little bit different information to tell us how well we're recovering parameters. Then we're going to save all of this in a list and output it to the file. And this is the other location where we need the replication number, because when we output this list of results for the simulation, what we're going to do is change the replication number so that it varies, so that we see each replication on our disk rather than overwriting the file each time. So that's the R file for the simulation. When we go back into the folder, what we will see is that there are 3 other files. We have the simulation job file. This is the job script for Argon, once again. So we're going to go into this. Pretty much every bit of information in this, with the exception of one section, is the same as the high performance job file. So first we need to put our email address here. Please don't put my address. I will put mine there. You put yours in the same spot. Next, one little difference is we're going to run this on the University of Iowa all queue. The all queue is the queue to run jobs in for high throughput analyses. I like it because what happens is it does not give you the same limit of 5 jobs at once. You can run lots more jobs. There is a limit. I'm not quite sure what that number is, but you can do a lot more than 5. Generally speaking, they start very quickly, and the big issue with the all queue is that if somebody who owns the resource wants to use it, you get your job evicted, which means it terminates without being run. But in the simulation study, that's fine. What we can do is check which simulations have not run at the end and rerun those through the all queue as well. So it's not a huge problem to run multiple replications on all queue. But then again, one other thing I'll note is if your simulation replications do take a little bit of time, all queue may not be the best for you. Using the UI queue may be better. Because the longer these simulations run, the more likely it is you get evicted. That's just part of the process of learning how to use the resources on the HPC. So that's one change. For each one of these analyses, we are going to also we're going to request 4 cores for each one of these analyses, just like we did before, but everything else is pretty much the same. I changed the name to IRT simulation. But finally, for this analysis, we get into the actual code of the analysis itself. We load R, we load JAGs, and then we use the R script command to run R. R script allows us to put command line arguments into R that will be captured by our R script using the command args function. So here, R script, we put the name of the file. This is IRT simulation rep.r. And then we put this command, $, capital SGE underscore, capital TASK underscore, capital ID. That is the replication number. So each replication number shows up right behind the file name. And then what happens when R starts to execute the script, this first command args function will grab that replication number and we'll save it and use it in our simulation. So once again, small differences on the file. We're using the all queue and we need to save, we use this command, the SGE task ID command, to save that last value. Finally, we have the name that's changed as well. So how do we submit this? That is where the other location of the difference happens to be. to submit an array job, we go back to the Argon terminal window, we type the word qsub again, but now we use the option -t, which tells us how many tasks to use. And we're going to use, we put the starting number of the task, a dash, and the ending number. So -t 1-10 means we're going to do 10 replications of the same script file, numbered 1 through 10. So each one of these will show up in the R when we're capturing the replication number. And then we put in the simulation.job file itself. When we submit that, it has been submitted. We're happy, should be happy, but let's take a look at the status, qstat-u. Right now, qw means it's waiting to run. And sure enough, there are all of our running jobs. In fact, if we switch over to mail, what we should see is that we have now 10 new emails. And this is where email is a little bit of a problem. If you're sending all of these job emails to your email inbox, you might have a ton of problems, because if you run a simulation that has thousands of replications, you're going to have thousands of emails show up. There's two ways to handle that. The first is to don't send email, right? If we go back to our job script itself, what you'll end up seeing is we can turn off email by just deleting this line or deleting either of these, but then you won't know when the job's finished. The second way is to put a filter in your email to filter all jobs from this root email address, root@hpc.uiowa.edu, and filter those so that they get moved to a different folder. That's what I do. I like the filter option. If you want to know how to do the filter, ask me. I will be happy to help you with that. Or maybe I'll make another video, or maybe both. We'll have to see. Suspenseful. Anyway, as I'm rambling on here, you'll note I received another 10 emails saying that all of my jobs were complete. So hooray. In fact, looking at all of them, each one of them has an exit status of 0, meaning all of them completed normally, which is great. None of them were evicted. Most of them took a little under 50 seconds to run. So again, not something that actually this is something we might use in HPC for, the high throughput, particularly if we're using thousands of analyses. So if we go back to our folder for our high throughput example, if we refresh the window, now you'll see we have a ton of files listed here. A ton of error files. If we click an error file, these actually show us the what was written to screen for all of this. This is just all the loading of all the packages. And the output file now talks about, it contains the convergence value, the thing we printed to screen from this cat command at the end of the model analysis. But what we also have are 10 different files consisting of our results for each replication. So if I wanted to look at the results for replication 1, if I clicked it, it'll load. Now I can examine the simulation results. I can type sim results, and when I just look at results itself, here are the different correlations, RMSEs, and bias values. In general, I don't like these numbers. They're not great. They're not ideal. That's part of the reason we only have 100 people. So it just gives us a little bit of information. That's a topic for a different time. The bigger issue is, how do we take each of these 10 files and consolidate them or aggregate them so we can look at the results overall? And sure enough, that presents us with a chance to do yet another high performance job. Remember, the high performance job is something where we do a long running or something that requires lots of resources on the machine. So what I did was I created an R script that we can run that will aggregate each of these files. This is an opportunity for us to use yet another job to do this. So I created the job script file called results job. This is a high performance job. Again, I can click on here, I can go and put my email address. And here I'm going to run it in the all queue, as it won't take a whole lot. I don't need JAGs because this is just using the base R commands effectively. So I don't have the JAGS part, and I just use R script to run this. And I'm actually running this with 1 core rather than 4 because there's nothing parallel going on to make this work. So if I go back to my Argon terminal, I can type qsub, and I can type it results.job. I can submit it. It has been submitted. I'm going to flip over to the email, and nearly moments, seconds after the email notification that it started arrived, 2 seconds afterwards, I received the email notification that it ended and it exited normally. So that means I can flip back to my R window, I can hit refresh, and what we'll find is the final results.r data. That is the final results of this analysis. When I click on that, you will see all of the final results. We have our values for correlation for each of our parameters, our RMSE for each of our parameters, and our biases. And what we typically do in a simulation study is somehow summarize the variation that we see in each of these. So that's a high throughput job. That's basically it. I found this incredibly effective at running simulations. When I started long ago in grad school, to run my dissertation, I actually bought a few refurbished Dell computers. I had like 4 of them in a back room in my house, and I plugged a keyboard and mouse. I had them facing backwards, and I plugged a keyboard and mouse into each of them separately, and it was a really inefficient process to run my simulation studies for my dissertation. Had I known about this at that time, my life would have been much better. So my job as professor is to try to make your life better, and the only way I know how to make your life better is through talking about this. So, if you found this useful, hit the like button. I've watched too much YouTube in this quarantine. Anyway, I hope this has been helpful, and I appreciate you watching. Thank you.